So, you should have some graph paper out by now. So, on your graph paper, step one, what I want you to do, sorry, it gets loud here. Step one, what I want you to do is I want you to create a right triangle with side lengths 1. Right triangle with side lengths 1. Go ahead and complete that right now. You have 30 seconds. You can listen to motorcycles for 30 seconds. Do it now. Get it done. Tick, tock, tick, tock, tick, tock, tick, tock. Hurry up. Okay, right triangle, side lengths 1. Gonna look something like that. Mine's really ugly and sloppy. Yours should be much prettier than mine, but I don't think anybody can argue with the fact, except for maybe Scotty, that this is a right triangle, and it does in fact have side lengths 1. Next, what I want you to do is next to this triangle, I would like you to use the Pythagorean theorem, that is a squared plus b squared equals c squared. The two legs squared and added together equals the hypotenuse squared. I would like you to tell me what is the length of that hypotenuse. So do that now. You have 15 seconds. Substituting in, we get 1 squared plus 1 squared equals our hypotenuse squared. Well, 1 squared is just 1, so really we just have 1 plus 1 equals 2, which is our hypotenuse squared. So C, our hypotenuse, has to be the square root of 2. An irrational number. A decimal that's going to go on forever and never repeat the same pattern. So, we just drew an irrational number. That's kind of cool. Alright, so next what I want you to do is I want you to draw a right triangle with legs of length 5. And once you do that, similarly, I would like you to tell me what is the radical exact value expression of the hypotenuse. So take 1.5 minutes and do that right now. Draw yourself a right triangle with legs of length 5, and then tell me what is the length of that hypotenuse. Write it as a radical expression. An expression meaning something with a square root sign. Go! So you should get some half of a square that looks like this, and you should find that the hypotenuse is the square root of 50. And we get that by going 5 squared plus 5 squared equals c squared. So we get 25 plus 25 is c squared. So we get 50 is c squared, and we take the square root of both sides to get the square root of 50 for the length of that hypotenuse. And now what I want you to do is I want you to tell me what I should say is I want you to simplify this number that we just found, the square root of 50, by a factor of this number that we found, the square root of 2. By which I mean, if you look at the length of this hypotenuse, well, the length of this hypotenuse is a bunch of these little square root of 2 bits. What I want you to do is I want you to tell me how many of those little square root of 2's equal the length of that hypotenuse, square root of 50. You have 30 seconds because I basically just did it for you. Hey, that's right. You're totally correct. We're going to get 1, 2, 3, 4, 5 of those. So we can say that the square root of 50 is equivalent to 5 times the square root of 2. What we just did was we simplified that radical expression, the square root of 50, to a more algebraically simple radical expression, 5 times the square root of 2. Geometrically, instead of referring to it as the length of the hypotenuse of a right triangle of side lengths 5, we've broken it down to the length of the hypotenuse of a right triangle with side lengths 1, a more geometrically simple representation. Something else that I want you to recognize is, keeping with the theme that we've had in this class as of late, these two triangles are similar triangles. They have the same dimensions. We've got side length 1 there, so our scale factor between these two is 5. Multiply this triangle by 5, those lengths become 5, because 5 times 1 is 5, and the hypotenuse becomes 5 times the square root of 2, because the hypotenuse there was the square root of 2, so we multiplied it by 5. Ooh. So what we're getting at is simplifying radical expressions. We want to rewrite complex radical expressions in a more useful way to us. Now, we don't want to just put ugly decimal approximations like that, because that's not very useful to us. Again, mathematics is quite often about recognizing patterns, and it's very hard to recognize a pattern in some string of very long decimals, but sometimes we can recognize patterns seeing things in simplified form much easier. So that's what today is going to be all about. Now, what I want to show you next is algebraically why this works, why we can simplify the square root of 50 down to something like 5 times the square root of 2. Now, before we do this, there are a couple things I want to talk about. The first one being just some basic rules that we have to follow / get to follow. Rules of algebra and rules of exponents and radicals. If you have the square root of a times b, you can rewrite that as the square root of a times the square root of b. That is, if you have, say, the square root of 25, you could rewrite that as the square root of 5 times 5, which you could split up into the square root of 5 times the square root of 5. Now, you probably don't want to do that. That's not very useful in this case, but know that you can. We're going to use that later on. So, you can always break whatever your number underneath your square root sign is, you can always break that up into factors. Now, another key idea here is prime decomposition. Basically, what that says, once I learn how to spell, what that says is whatever number you give me, don't care what it is, say it's 32, you can always break that up into a product of prime numbers. For example, 32 is an even number, so I can divide it by 2. I could write that as 2 times 16. 2 being a prime number. Well, I can keep going, and I notice 16 is also an even number. So again, I can divide by 2. So I can write this as 2 times 2 times 8. Well, I can keep this going again. 2 times 2 times 8 is just 2 times 4. And then one more step. 2 times 2 times 2 times 4 is 2 times 2. So the distinct prime decomposition of 16 is 2 to the power of 5. Now that was kind of a stinky example because it's not always going to be the same number like that. So let me show you one more with a different number. Let's say 20. 20, again, it's even, so I can definitely divide it by 2. So I can write that as 2 times 10. Well, again, 10 is even, so I can write that as 2 times 10 is just 2 times 5. Now notice this would be the distinct prime decomposition of the number 10. When you break it down into prime numbers, it's just 2 times 2 times 5. Which is, of course, 20, because 2 times 2 is 4, and 4 times 5 is 20. Now, you don't have to divide by 2 in the beginning each time. I could have started by, say, dividing by 4 and gotten 4 times 5. But the key is, once you have a prime number, you can't take that any farther. But if your number is not prime, you can always break it down more. 4 is just 2 times 2. And you should always get the same prime decomposition no matter how you work this out. The reason this is important is because one method we can use to simplify radical expressions is by finding prime decompositions. That is, take a look at the example we looked at, the square root of 50. Let's break that number, 50, into its prime decomposition. And again, there are always going to be multiple ways you can go about doing this. You just got to do it whatever way seems to make sense for you. So for me, I look at that, I'm like, well, 50, well, let's divide that by 10. Well, 50 divided by 10, we get 5 times 10. Still the same exact thing. 5 is a prime number, so keep going with 10. Well, 10, you can also write that as 5 times 2. So we got 5 times 5 times 2. And again, check yourself. 5 times 5 is 25. 25 times 2 is 50. This is the prime decomposition of 50. 5 times 5 times 2, all prime numbers. But remember, we were dealing with square roots here, so that is all still valid. Essentially, all we've done is we've rewritten the square root of 50 as the square root of 5 times 5 times 2. Totally fine, haven't done anything yet. Let's use those rules we had before, and let's split that up to the square root of 2 times the square root of 5 times the square root of 5. Well, square root of 5 times the square root of 5 is like saying square root of 5 squared. And we're just going to simplify to 5 square root of 2, because the square root of 5 squared is just 5. And we should expect that, because that's what we already showed geometrically. So, if you choose to simplify radicals using the prime decomposition method, the key is you're looking for pairs of prime numbers in the prime decomposition. Another way to think about this, a way that might be a little bit simpler than going to prime decomposition, is to look for perfect square factors. Alright, so quick trip down memory lane. Remember that a perfect square number are the numbers, the integers squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared 16, 5 squared 25, etc., etc., etc. 36, 49, 81, miss 64, and 100, all that good stuff. Go on forever and ever and ever. There are infinitely many perfect square numbers. They just get really big really quickly. Now, the key here is to try to break the number that you're trying to simplify, square root of 50. Try to break that 50 down into perfect square factors. That is to say, let's try to rewrite this with one of those numbers factored out, if possible. So you should be able to look at that pretty quickly and know which will work. But if you don't, just check yourself. Well, 50 divided by 4 is 12.5, so that doesn't work because you get a fractional answer. 50 divided by 9 is 5.55555 repeating forever, so that doesn't work. 50 divided by 16, 3.125, also doesn't work. But we know that 50 divided by 25 is 2. So 25 times 2 is the same as 50. And so we can say that the square root of 50 is equal to the square root of 25 times the square root of 2. We factored out one of those perfect square factors because, well, we can simplify that. The square root of 25 is 5, so we get 5 times the square root of 2. Again, same exact end, but I think a little bit more elegant of an approach to solve that problem. So go ahead, let's do one example of this together, and then the rest of the time will be yours to work. So go ahead and I'll show you this next problem. What I want you to do is I want you to simplify the radical expression square root of 26,460. Big ugly number. Use whatever method you prefer, but I would probably recommend trying to factor out perfect square factors. So give it a shot. We'll go 2 minutes on this. Try to reduce this to simplest radical form. Okay, so let's go ahead and start to reduce this, simplify it, I should say. Again, there are multiple ways to do this. There's no one right way or one wrong way. You just kind of got to start going. We want to see what are the factors that we can factor out of this that are perfect square numbers. Well, since this is such a big number, chances are we're going to have one or a couple large prime factors in there that we can factor out. So it might be a good idea to try big and then work your way down, but it's also a safe way to start small and work your way up because we know 26,460 is even, so we can definitely pull out a factor of 2. So that could be a good place to start. It's kind of up to you. I'm going to start big, and if I try to see if the perfect square factor 81 is in there, the perfect square number 81, 9 squared, do 26,460 divided by 81, you get 326 and 2/3. So since it does not divide evenly, we know that 81 is not a factor of 26,460. So let's maybe try a lower one. How about, well, 8 squared, 64. 26,460 divided by 64, well, you get 413.4375. Again, not a whole number, so it doesn't work. Let's try the next one down, 49. Do 26,460 divided by 49, and you do indeed get a whole number. You get 540. So we know I can split this up into the square root of 49 times the square root of 540. And again, the whole point of that being, I know that the square root of 49 is 7. So I get 7 times the square root of 540. Now, we're not done yet because I can still simplify some more. So keep looking for more factors, more perfect square numbers that you can factor out of 540. Well, does 49 work again? If you do 540 divided by 49, no, you get 11.02. So again, try something smaller again. We already know those bigger numbers won't work, otherwise they would have factored out evenly before. So what's below 49? Well, 49 is 7 squared, so let's try 6 squared, which is 36. So take 540 divided by 36, and look, you get 15. So again, we can rewrite this as 7 times the square root of 36 times the square root of 15. Again, we can simplify the square root of 36 to 6, so we get 7 times 6 times the square root of 15, which is, of course, 42 times the square root of 15. Well, how do you know if you're done or not? Well, are there any perfect square numbers in 15 that we can factor out? No, there aren't, because 42 square root of 15, if you write 15 in its prime decomposition? Well, that's just 5 times 3, and they're both prime numbers, so we cannot reduce this any further. So that is our completely simplified answer, 42 times the square root of 15. I know sometimes you look at this and it might seem like, well, that doesn't look any better than the square root of 26,460, but to a mathematician, it does, because again, it might help us recognize patterns later on down the line, leaving it in exact form rather than rounding your answer. So, your goal for the rest of the class period is to work on the worksheet that will be handed out to you shortly. Anything that you do not finish in class will be homework and will be checked on block day when I am back. So let me finish this by showing you a picture of where I am, so maybe you can appreciate how beautiful it is. Sorry I'm not with you, but I'm actually not here because I'm on the road now, so that's kind of lame. But this is the beautiful hillside behind my cabin. There you go, and I will see you tomorrow, or maybe the next day, or whatever.